Imagine everything you know, the planets, stars, galaxies, even time itself, compressed into a point smaller than an atom. This point, known as a singularity, held all the mass and energy of the universe in an incredibly dense state. This unimaginable state is where our universe began, a moment of infinite density and temperature. An idea so profound it's called the Big Bang, marking the birth of everything we know.
Around 13.8 billion years ago, this singularity didn't just sit still. It erupted with unimaginable force, a colossal explosion that set the universe into motion. This explosion set the universe on a trajectory of expansion and cooling that continues to this day, a process that has shaped the cosmos over billions of years. Evidence for this monumental event lies in the faint afterglow of the Big Bang, a cosmic microwave background radiation that permeates all of space, a relic of the universe's fiery birth.
Like the fading embers of a colossal explosion, this radiation tells a story of a hot, dense universe in its infancy. This early universe was a seething cauldron of energy and particles, a place of intense heat and density. The Big Bang wasn't just an explosion of matter into pre-existing space. It was the expansion of space itself, carrying galaxies along for the ride like driftwood on a rushing river, a cosmic journey that continues to this day. This expansion is not just a movement of galaxies, but the stretching of space-time itself.
The early universe was a chaotic place, a seething cauldron of energy and particles, constantly interacting and transforming. As the universe expanded and cooled, energy condensed into matter, following the principles of physics. This transformation followed Einstein's famous equation E equals mach squared, which describes how energy can become matter. Subatomic particles like quarks and electrons formed, eventually combining to create the first atoms, mostly hydrogen and helium. These atoms, the simplest elements in the universe, were the building blocks for everything that followed. These atoms, forged in the crucible of the Big Bang, would become the building blocks for stars, planets, and eventually life itself. Understanding the Big Bang is fundamental to grasping our place in the cosmos.
It's a reminder that we are part of a universe much grander than ourselves, born from a single event that continues to shape the cosmos today. The story of the Big Bang is the story of us, a tale of cosmic evolution that has led to the universe we inhabit. From the smallest particles to the largest galaxies, everything traces its origins back to this explosive beginning. It's a humbling reminder of our place in the vast expanse of the universe, a testament to the power of scientific discovery. The Big Bang continues to shape the cosmos today, a dynamic and ever-evolving universe that we are just beginning to understand.
After the initial burst of energy and particle creation, the universe entered a period known as the Cosmic Dark Ages. This was a time of profound silence and stillness, a stark contrast to the explosive birth of the cosmos. This era, lasting hundreds of millions of years, was characterized by darkness, as the universe, still incredibly hot and dense, was filled with a fog of neutral hydrogen gas that prevented light from traveling freely. The universe was like a vast, impenetrable ocean of darkness with no stars or galaxies to pierce the gloom.
Photons, the particles that make up light, were constantly scattered and absorbed, like beams from a flashlight lost in a dense fog. This scattering meant that any light produced was quickly absorbed and re-emitted, never traveling far enough to illuminate the cosmos. During this epoch, gravity began to exert its influence, slowly drawing together clumps of hydrogen and helium. These primordial elements, formed in the first few minutes after the Big Bang, began to coalesce under the force of gravity, creating regions of higher density. These regions of slightly higher density, like seeds in fertile ground, would eventually become the birthplaces of the first stars and galaxies. Over time, these clumps grew larger and denser, setting the stage for the next great transformation of the universe.
The universe, though shrouded in darkness, was preparing for a spectacular transformation. It was a cosmic dawn waiting to break, a silent prelude to the symphony of light and life that would follow. Although we can't directly observe this era with our telescopes, as no stars or galaxies existed yet to emit light, scientists study the cosmic dark ages through simulations and by analyzing the faint afterglow of the Big Bang. These simulations help us understand the conditions and processes that led to the formation of the first stars and galaxies.
This cosmic microwave background radiation carries subtle imprints of the density fluctuations present during this time, providing clues about the seeds of structure that would eventually give rise to the universe we see today. By studying these imprints, scientists can piece together the story of how the universe evolved from a hot, dense state to the vast, complex cosmos we inhabit. The cosmic dark ages represent a crucial transition in the history of the universe, a bridge between the formless chaos of the Big Bang and the emergence of the first luminous objects that would illuminate the cosmos. This period set the stage for the formation of the first stars, galaxies, and eventually, the complex structures that make up the universe today. It was a time of profound change, a silent prelude to the symphony of light and life that would follow.
As gravity continued to draw matter together, the dense clumps of hydrogen and helium in the early universe reached a tipping point. The immense pressure at their cores triggered nuclear fusion, the process where lighter atoms combined to form heavier ones, releasing tremendous amounts of energy.
This marked the birth of the first stars, colossal balls of hydrogen and helium, much more massive and luminous than our own sun. These first stars, often called population 3 stars, bathed the surrounding universe with intense ultraviolet radiation, ionizing the neutral hydrogen gas that had shrouded the cosmos in darkness.
This epoch of reionization marked a profound shift, as light could now travel freely through the universe. The cosmos, once dark and opaque, was becoming transparent, allowing us to peer back into its distant past.
As more and more stars ignited, they clustered together under the influence of gravity, forming the first galaxies. These early galaxies were smaller and less structured than their modern counterparts, often colliding and merging to create larger and more complex systems.
The universe was transforming from a sea of darkness into a dazzling tapestry of light and structure. The formation of the first stars and galaxies marked a pivotal turning point in the evolution of the universe. It not only filled the cosmos with light, but also seeded the universe with heavier elements, the raw materials for planets, life, and even ourselves.
Section 4. A Cosmic Ballet, the Dance of Galaxies and the Growth of Structure. Following their formation, galaxies didn't remain static. They embarked on a grand cosmic ballet, driven by the relentless pull of gravity.
Over billions of years, galaxies interacted and collided, their gravitational forces sculpting them into a stunning array of shapes and sizes. Spiral galaxies like our own Milky Way formed with majestic arms of stars and gas, while elliptical galaxies took on smooth, rounded forms.
The expansion of the universe, set in motion by the Big Bang, played a crucial role in this cosmic dance. As the universe expanded, it stretched the fabric of space-time, influencing the distribution of matter and the evolution of galaxies.
Gravity counteracted this expansion, pulling galaxies together into clusters and superclusters, vast cosmic structures connected by filaments of dark matter, a mysterious substance that we can't see but which exerts a gravitational pull.
This interplay between gravity and expansion has shaped the large-scale structure of the universe, creating a cosmic web of galaxies, clusters, and voids. The universe is not a random scattering of objects, but rather a complex and interconnected tapestry, woven together by the invisible hand of gravity. Section 5. Birth of a solar system. Our sun ignites and planets form. Within the Milky Way galaxy, about 4.6 billion years ago, a remarkable event unfolded, the birth of our solar system. This event marked the beginning of a journey that would eventually lead to the formation of the planets, moons, and other celestial bodies that we observe today.
A giant molecular cloud, a vast collection of gas and dust, began to collapse under its own gravity. This collapse was triggered by a disturbance, possibly a nearby supernova explosion, which caused the cloud to fragment and contract. As this cloud contracted, it started to spin, and the material at its center coalesced to form a protostar, the precursor to our sun. The spinning motion caused the cloud to flatten into a disk, with the protostar at its center, surrounded by a rotating disk of gas and dust.
The protostar continued to accrete material from the surrounding disk, its core temperature and pressure steadily increasing. As more material fell onto the protostar, it grew hotter and denser, eventually reaching the conditions necessary for nuclear fusion. Finally, the critical threshold for nuclear fusion was reached, and our Sun burst into life. This ignition marked the transition from a protostar to a main sequence star, releasing immense energy and light.
The Sun's powerful gravity drew in most of the remaining material in the disk, but a small fraction remained, orbiting the newborn star. This leftover material would eventually coalesce to form the planets, moons, and other small bodies in our solar system. Over millions of years, these remnants collided and clumped together, gradually forming planets, moons, and asteroids. The process was violent and chaotic, with countless collisions and mergers shaping the young solar system.
Close to the Sun, where temperatures were scorching, rocky planets like Mercury, Venus, Earth, and Mars formed. These terrestrial planets are composed primarily of rock and metal, and their formation involved the accumulation of solid materials in the inner solar system. Further out, beyond the frost line, where it was cold enough for ices to remain solid, gas giants like Jupiter and Saturn formed, along with ice giants like Uranus and Neptune. These planets accumulated large amounts of gas and ice, becoming the massive giants we see today.
The formation of our solar system was a chaotic and dynamic process, a delicate balance between gravity, collisions, and the influence of the young Sun. The interplay of these forces shaped the diverse array of celestial bodies that populate our solar system. From this maelstrom of creation emerged a diverse array of planets, each with its own unique story to tell. The early solar system was a place of constant change and evolution, setting the stage for the development of the complex and varied planetary system we observe today.